All right, good morning, everyone. Let's get started. So today we're doing our last set of talks on perception. And our first speaker is Nancy Kanwisher. And Nancy Kanwisher is professor of cognitive science, of brain and cognitive sciences at MIT and the McGovern Institute. People always say, someone doesn't need that the person doesn't need an introduction, but I think Nancy literally doesn't need an introduction. I will mention just very quickly that we all know how accomplished Nancy is in cognitive sciences. If you ever get the chance to talk to her offline, ask her about her life story, because she also has this kind of set of really inspiring life story, doing humanitarian work, and all these things that I had no idea about until I had known Nancy for about 10 years. Yeah, so please welcome Nancy.
Thanks. Thanks, Julian. And huge thanks to Ilker and other organizers. This has been super fun. I'm just really loving this conference. I don't have a lot to say about efficiency, except for something that's so obvious and so like me to say, but I'll say it anyway. And that is that I would think that AI researchers interested in efficiency might learn something by looking at the functional organization of the brain. And here's my ridiculously oversimplified schematic diagram, the point being that the human brain has a striking degree of modular organization with different bits that do different things. And although I know it's currently popular, especially in systems neuroscientists studying mice, to say that everything is everywhere in the brain, everything is not everywhere in the human brain. Thank you very much. And presumably the reason we have this kind of organization is that, as Leslie mentioned the other day, different kinds of functions that humans do, like navigation and face recognition and understanding language, require very different kinds of representations and algorithms. And so maybe it makes sense to implement them in different bits of tissue. Okay, and so maybe this is closely related to what Tyler was saying yesterday with the idea of that we could sort of augment the model synthesis architecture with some cached components. I'm not sure. We could talk about that offline. Okay. So it seems to me that it's a good bet that this modular organization has something to do with efficiency, no matter how you define it. And I will just leave it at that for now and say that today I'm going to talk about a possible addition to this menagerie of brain regions, a set of regions in the parietal and frontal cortex that seem to be involved in something like intuitive physical reasoning. Excuse me. So to start, what do I mean by that? Let me illustrate it with a really simple general idea with a very simple image. If you look at this image, within a few hundred milliseconds, like maybe 200 milliseconds, you've already figured out there's a fork, there's a glass, there's a table, there's some OJ, and there's a placemat. But within maybe another 100 milliseconds, or maybe within those first 200 milliseconds, very quickly, you've also probably processed the fact that the glass is supported by the table, that it contains OJ, that it could be picked up, but might spill, and then would stain the placemat, right? So all this kind of stuff that goes beyond just what is where. So that's the point. Vision is a whole lot more than just what is where. It includes determining physical relationships between objects, action affordances, which just means what can you do in this scene, and possible future states. And that is the rule, not the exception. If I show you an image like that, everybody immediately has a reaction. I don't even need to ask you a question about it. You see a cup in peril. This is even worse. And if you see an image, if you walk into a scenario like this, you just immediately know not to press here, but to press there to make the door rotate. And you can see that trouble is about to ensue here. Okay, so point is that we make intuitive inferences about the physical world frequently, rapidly, apparently effortlessly, quite automatically. And as the people who really started this whole line of work way back in the, 80s, maybe even 70s, René Baillargeon, Liz Spelke, studying cognitive development in infants, showing that many of these abilities are present very early in development. They're essential for understanding what we're looking at, for planning any action, and for predicting what will happen next. So the question is, how do we do all that? And in very simplistic outlines, there are two ends of a spectrum of how people have thought about possible computational models of human intuitive physical reasoning. One is the kind of reductive view that it's just pattern recognition. So maybe something like Adobe feed-forward CNN type thing could take visual images and extract a lot of the relevant information quickly. In that sense, it's really part of immediate seeing, right? And so you might have, and on this view, the physical information you extract will be closely tied to the visual features that predict that information. So for example, in this case, maybe all you have to do is detect some kind of visual overhang, and that's enough to know possible falling event ensuing or something like that. And so how far that kind of account will go, who knows, but it's at least one kind of caricature of a simple view. At the way other end of the spectrum, we have rich, structured, generative models of the world, of the kind that Josh has been putting forth, and that and many of his collaborators, and that has a long history in cognitive science, going back to Craik, and probably if you look far enough, the Greeks. But I'm not a scholar, so I don't know. And on this view, the idea is that what we represent is much richer and more abstract. We represent the physical properties of objects and the relationship between objects, things like mass and whether objects are in contact with each other, that those representations would generalize to new scenarios, and that those representations would enable us to make forward simulations of what's going to happen next. And in Josh's wonderful phrase, this is kind of like a game engine in the head, right? That predicts what's going to happen next when you play a video game to produce a nice realistic simulation. The idea is maybe we have one of those in our heads to predict to understand and to predict what's going to happen next. So, does the brain have a physics engine? Or do we use something like the machinery in the ventral visual pathway that's kind of pretty well modeled by this kind of a view, at least to a first approximation? I know there are a lot of people who will tell me not really, not fully, I get it, but something more like that. And so we can make some predictions. If the brain has something like a physics engine, we should be able to find brain regions that are selectively engaged when you do physical inferences, right? That's the usual game we play with functional MRI. Those regions should also have abstract information about physically important stuff, like the mass of objects, which is just the most basic physical property that determines how objects will behave, how they will react to other forces, and what forces they will impart on other things, right? F equals ma and all of that, right? It might also have information about whether objects are in contact with each other, another thing that infants can process very early, and that's important for predicting what will happen next, because contact relationships tell you how to predict what's gonna happen, right? If I stick an object on top of my phone, this is a terrible example, and I move the phone, the object goes with it, right? So knowing that one object supports another enable us to predict how the supportee will behave when the supporter is moved. Okay. Also, importantly, these regions should be able to do some kind of simulation or at least prediction of what will happen next. And we might also predict that the same brain systems should not be present, that these systems should not be in the ventral visual pathway, because, as I mentioned, they're pretty well modeled by these kind of more largely feed-forward-y, feature-y kind of visual representations. And they might not be extracted by simple image or video-trained artificial neural networks. Okay, so let's start here. So this starts with work around a decade ago now with Josh Tenenbaum and my then postdoc Jason Fisher, who's now a faculty member at Coimbra in Portugal. And so what Jason showed is that if you scan people, you can find a set of, with functional MRI, you can find a set of regions in the parietal and frontal cortex, shown here in a few subjects, that respond more when we do a version of Josh's famous tower task. So you see a video of this object rotating, and you're asked whether, when that tower falls, will there be more blocks on the red side or the green side of the table? That's the physical task. The control task that you do on the same stimuli is to say whether there are more blue or yellow blocks. And we match that for difficulty by reaction time and accuracy, okay? And so these regions all respond more when you do the physical task than the color task in this contrast. So, okay, that's cool, but who knows? Got to try other things. So another thing Jason did, so this is just the response to the physics tasks and the color tasks and a bunch of different subsets of those regions. Okay, Next, we said, okay, well, before we had the same stimulus with two different tasks. Let's have the same task with two different stimuli. So Jason made these animations in which the red and blue dot, I've lost the video, I'm sorry about that, but the red and blue dots are moving around in a very physical way, bouncing off each other and against the walls of the square and the objects in it, like billiard balls. You just look at it and you can immediately tell these are just physical objects interacting physically. Versus the same two dots are moving like animate agents, chasing and fleeing and flirting and such, also immediately evident within a second of the video starting. You can see these are animate agents interacting. And in both cases, what you have to do is like look at it, and then one of the dots disappears, and you have to predict the trajectory of the other dot that's no longer visible. And when you do that, you see the same regions more engaged with the physical understanding and prediction than the social understanding and prediction. And then third, we recycled some old localizer data because we realized that our object conditions we had these videos for mapping out face and place and body areas and the ventral pathway, and we realized the object conditions were very physical. There were objects interacting physically. So let's recycle those old data. And in fact, these same regions respond a whole bunch more when you just look at 3-second video clips of objects interacting with each other compared to video clips of faces or bodies or other things. Okay, with just passive viewing. Stuff like that versus that. Okay, and here's some data from one of the studies showing higher response in those regions when you just look at physical videos versus social videos. Okay, and those of you who think about the brain a lot might look at that and say, hey, I've seen those regions before. Isn't that just multiple domain cortex? I worried about that for years before we finally got serious and looked. And quite to my surprise, those regions overlap a teeny bit. Multiple domain cortex, for those of you who are not deep in this idea is that in addition to all these highly specialized regions that I tend to obsess about, there are also big swaths of parietal and frontal cortex that are very, very domain general, right? So they seem to engage almost whenever you do anything difficult at all, almost no matter what it is. And they look a little bit like that. So we finally scanned subjects individually with localizers for multiple domain cortex. A standard version that we've been using for a long time is a spatial working memory task that has a difficult condition and an easy condition. And we get the multiple domain regions, but they overlap only a teeny tiny bit with the intuitive physics regions, to my surprise and delight. I don't know if that was clear enough. Did people get that? Just stop me if I'm saying things that don't make sense. Okay. So all of this is consistent with the hypothesis that these brain regions implement our understanding of the physical world, which is based on a generative model that can run forward simulations to determine what will happen next, akin to the physics engines in video games. Okay, but it doesn't show that at all. It's just consistent with that hypothesis. And to try to test it more stringently, we can make some more predictions. Well, okay, those are the things I just showed you. And also importantly, those regions that show these signatures of intuitive physical reasoning are miles away from the ventral visual pathway involved in object recognition. So they're really clearly different from that system. And they're also distinct from this multiple domain cortex. Okay, so our strategy from there has been, okay, we can find this set of regions pretty easily in each subject individually with this contrast of the physical versus color task on the tower stimuli. And so we've been using that as our localizer to identify those regions so that we can then ask them new questions. And for those of you who don't do functional MRI, the reason to have a localizer is that there's a lot of anatomical variability from one subject to the next. And so if you want to study what a region does, you have to first find it in each subject. And then once you found it, then you can ask that region new questions. Okay? So we're using this as our localizer, not for any deep reason, just because it worked and we're using it for now. And maybe someday we'll come up with something different, but we're using it for now. Okay. So then we can now ask some of these other questions. Do those regions contain abstract information about mass, about the relationships between objects? Do they do prediction, et cetera, et cetera? Okay. Okay, so how do we look for information in the brain? I'm sure most of you know this already, but in case anybody has not been involved in this. We use always the simplest possible analysis. I have a simple mind, and I don't like to do anything fancy, and so this is what we do. This is multiple voxel pattern analysis, the simplest possible version of it. You collect a bunch of functional MRI data in terms of the response across voxels within a region in two different conditions. In this case, when people are looking at a light object, for example here, okay, that's a light object versus a heavy object, like that, okay? And in each case, you scan people looking at a bunch of videos like this, and you get some pattern of response across voxels in each condition, okay? And then to see if it's an abstract representation, we look at other scenarios that also depict a light object, like that, or a heavier object, like that. And we collect the pattern of response across the same voxels there. And then the idea is, if that region that we're looking at, that's shown with these fake data voxels here, if it contains abstract information about mass, we should find that the pattern of response should be more similar within a mass, light to light, and heavy to heavy, than it is between masses, heavy to light and light to heavy. So we just look at the correlation of the pattern of response across those voxels and ask whether it's more, whether that correlation is higher within than between masses. Cool? Okay. So Sarah Schwetman, working with me and Josh, did these experiments and found that, yes, indeed, she could decode mass, at least this simple version of heavy versus light, in each of these regions, and importantly, she could decode it across objects and scenarios. So these are very abstract representations. And also she could do this even when subjects were not asked about mass. They were just looking at the videos, okay? Or actually, in some cases, doing an orthogonal judgment on the color of the objects or something like that. Okay, so that's cool. What about other kinds of information that we might want to look at in these regions? So Pramod looked at whether you could decode from those regions, that is, whether they have information about whether objects are in contact. And so he made a bunch of videos like this, where you see an object being placed in contact. In that case, it's containment. And then you show the consequences of containment, namely that the objects move together. Or in this case, it's support and the consequences of support. And then there's control versions of each, where you do a similar action, but they're not in contact, and so they don't have contingent action, right? And so we scan people looking at these things, and then do the same multiple voxel pattern analysis decoding thing across different scenarios. I'm not showing you all the videos, but they're different scenarios. Some of them are Blender videos without a hand. They're different objects. They're really quite different. But in all cases, we're cross-decoding, that is, finding abstract information about contact versus no contact in this physics network, right? And not importantly in V1, which is some kind of indication that it's not just some visual low-level thing, not in the ventral pathway, not in LOC, et cetera. Cool? Okay. So yes, there's contact. There's information about the presence or absence of contact in those regions. But to me, one of the kind of more core questions about the possibility that this is a physics engine in the brain is that it should make predictions about what should happen next. So for example, if I show you a video like this, you probably have some kind of intuition that you extrapolate what's going to happen next. So the question is, does that extrapolation happen in those physics regions? And to find out, we scan people looking at loads of videos like this. They're very different scenarios. They all have an imminent collision or an imminent non-collision, where that object is moved over and it's not on a collision course, and an actual collision or an actual miss. Okay, so you either do it in the predicted case or the observed case. People are not asked to make predictions, they're just asked to look at the videos. Okay? And when we do that, in fact, we can cross-decode from observed to predicted. And what that means to me is that when you see this predictable collision, you are mentally extrapolating some version of the observed collision, as expected if you're making the prediction. Okay? And again, we see that in the physics regions, not in V1 and not in the ventral visual pathway. Cool. Okay. And again, these are across very different scenarios, different objects. You know, in another case, there's a cup on a table and an object that's flying through the air, either going to land in the cup, or it's going to or it goes in the in the other direction and goes off into space. And we can cross-decode it across directions of motion and all the different things that we've forced it to generalize. There seems to be just abstract information about predicted collisions and observed collisions. Okay, so all of this is consistent with this idea that we have a rich, structured, generative model of the physical world in our head that has abstract information about mass and contact, that generalizes to different scenarios, and that enables forward simulation like a game engine, although I point out that at least it's prediction. One can imagine doing prediction without actual simulation. I think that's really important. I would love to do a better test of that. We're trying, we're not there yet. Okay, but at least prediction. Okay, so, and also all of these things are found in the dorsal pathway, not the ventral pathway. And so that's also consistent with this idea that these things are being done by some more structured model. But you might be wondering, well, can't simple end-to-end trained models that don't have a rich internal structured physical model do the same thing? And so Georgina Wu, who's a postbac in my lab, has been working with Pramod, testing a bunch of artificial neural networks on her stimuli to see whether those ANNs can do these tasks. And so she's using, all the latest things that you guys have heard about. And so the performance on these tasks is not zero in these ANNs, but it's not very good, and it's weirdly uneven or jagged across conditions. Unlike humans, for whom, if you ask people behaviorally, these things are all trivially easy to perceive and understand. Okay. So we tested these same stimuli on contact versus no contact. They perform badly on predicted collision versus non-collision. They also perform badly, again, not zero, but badly. We tested vision language models. They're a little better, but still not great. Okay, so there's much more to be done on all of that. And you never want to say these models are never going to be able to do it. That's a risky proposition. But right now, they are lagging behind what the brain seems to do and what we can decode from the physics regions. Okay, so does the brain have a physics engine? I would give it a resounding maybe, okay? There's a lot more to be done. I know it sounds like I'm at the end of my talk. I'm not. I just didn't bother to retool this in a way that made it clear that I have a whole bunch of other weird little add-ons that don't really fit. So here come the weird add-ons. Okay. I know people need to pace themselves. It's like you think the talk's going to end, and then it goes on and on, and you're like, I thought you were going to end. Okay, at least that happens to me. Okay. What is the scope of engagement of this thing? So far, we've only tested it on a pretty narrow range of stimuli. They're all rigid objects presented in images and videos. And so that leaves wide open whether these things are also involved in processing non-rigid objects or fluids, whether they process auditory information. Maybe they're even engaged in when you process language, if it's language describing physical events. Okay, so just briefly, Vivian Powlin, working with Pramod, did this lovely study that was published last year that I'll just mention briefly. Vivian is a master of making the most beautiful stimuli, I think, in the history of my lab. Here's some examples. She made many of these. Here's a rigid object. Here's a non-rigid object. Also a thing. It's a coherent thing. It's just not rigid. Here's a fluid. This one is granular. And here's a liquid. And so she made loads of these, and they're all different kinds of colors and different transparency, and they are interacting with different physical environments, and they're just fabulous to look at. And so what she finds is in those physics regions, these labels are minuscule. These are the two thing conditions, the rigid and non-rigid objects. Here are the two fluid conditions, the granular and liquid cases. So these regions seem to be more engaged when you process things than stuff, right? And very delightfully, right next door, a little bit inferior in the brain to those regions, is a region that has the opposite response profile. And so it's a little bit, it's not the most whopping thing ever, but it's a, very significant partial double dissociation. And we think that's cool because my understanding is that game engines and simulators process fluids and solids separately, with particles for fluids. And so you might imagine there are very different kinds of representations and algorithms, and maybe there are also in the brain. Okay. All right, partial dissociation. What about auditory physical events? Well, I am kind of bummed out to report that so far our pilot data show no response in these regions to physical events in audition, like glass shattering and objects dropping and stuff like that. But I don't believe it yet. So stay tuned. We're still kicking the tires on that, and we do actually, weirdly, in other conditions, see that, again, just pilot data. If you show just the auditory correlate of an event versus just the visual video of the event versus both at once, there's an additive effect. So the auditory thing adds to the visual thing, but it doesn't seem to produce its own response. We don't understand it yet. We'll see. But I think it's important because, well, it's also relevant to this distinction between, what is it called, physics and graphics, in the, for those of you who know the Tomer Ullman's beautiful work on that. So I think it's important. We have to figure it out. What about language? Okay, and I'm going to go a little bit off the deep end by saying that this is relevant not just for our understanding of what the physics regions are doing, but to the much broader question of what does it even mean to understand language? I told you it's going to go off the deep end. Here we go. Obviously, people have been thinking about that for a very long time. And if we think about this schematic picture I started with, Ev Fedorenko has shown very beautifully over the last 10, 15 years that the classic language regions, these things in the left temporal and frontal lobes, are actually extremely specific for language per se. All kinds of other mental tasks that you might have thought would engage the language system, like music or arithmetic or holding information in working memory or pretty much anything. Perceiving gestures do not activate those regions at all. It's remarkably specific. Okay? Further, she and others have shown that those brain regions are pretty well modeled by large language models. That is, you can do this kind of encoding model game and predict responses in those regions to new held-out linguistic stimuli. That's pretty cool. Suggests some kind of similarity between those regions and the large language models. And also, it's increasingly clear that large language models capture some kind of real understanding of language. The meanings of words, the meanings of sentences, syntax, they capture a lot, right? We don't want to go overboard trivializing what they're really able to do. It's pretty impressive. But at the same time, they fail at many tasks that are trivial for humans, including physical reasoning tasks presented in language that humans can solve very easily. Many of the large language models are not good at this. And I mean the large language models that are trained on only language. I think those are the interesting cases here. Okay, so the idea here is that the core language regions in humans, similarly, like large language models, process relatively shallow understanding. A real understanding, but it's not, it's not really rich, okay? To achieve a deeper understanding of the content of language, the idea is that maybe we have to export information from the language system to some of these other regions that can build rich models of the stuff described in language, okay? So this builds on many very related ideas. It's not entirely new. And so there's one case where we know that this happens, and that's the right to TPJ that Rebecca Sachs has studied for a long time, that's very selectively involved when you think about what other people are thinking. And all of Rebecca's original experiments use language stimuli to show this, right? So you read a few sentences that either explicitly describe or can only be understood by thinking about what the agents are thinking about, and you get very selective engagement of those regions. So clearly the information has to come through the language system and be processed there, but then it activates this other region, which is actually in the other hemisphere. I just stuck everything on one hemisphere for ease here. Okay. Okay, so that's a case where we know that this exportation must happen, because we can see it land, come in over here and land over there. Okay. And so the hypothesis here is that maybe this is generally true. We're calling this exportation hypothesis, that deep understanding of other aspects of language may require building models in some of these other specialized brain regions. And so for present purposes, the question is whether that happens in the physics system. So can language engage those physics regions, and maybe when we need to process the linguistic information at a deeper level? Okay, I have no idea how I'm doing time. I have a bunch more. Am I okay? Will you just give me a 5-minute warning and I'll go from there?
You got
I got loads of time?
9 minutes.
Okay, good. I think I'm going to be okay. All right. So can we engage those physics regions by language? So Pramod started working on this quite a while ago, and he generated, sorry, these are too small to, I'll read it in a second. He generated a bunch of little text problems that are not very hard, but that either require you to answer questions about physical scenarios or social scenarios. So for example, the physical ones, here's an example. The Amazon is known for its yearly torrential rains. These rains last for weeks at a time without stopping, and they run into surrounding rivers. Dams were built to harness the water's force to turn huge turbines that generate electricity. What turns the huge turbines? The water, the electricity, or both? So you have to answer that question, just to make sure people are tracking. Example, social scenario. Sarah attended a work party with Leighton and Paul. Leighton slurped his drinks, laughed too loudly, and insulted her boss. Paul told funny jokes and engaged in deep, dynamic conversations with other guests. Sarah left the party embarrassed. Who embarrassed Sarah? Leighton, Paul, or both? Okay, so just little, scenarios like that. So people lie in the scanner, they read these things, they answer the questions. And so to me, the agenda was to see if we could get differential engagement of those physics regions by the physical language scenarios more than the social ones. But the backstory of this experiment was that actually it only really happened because my wonderful colleague Laura Schultz, who I never collaborated with, weirdly, had told me there was a new postbac arriving at MIT, Jessica Chomick, and we needed a project for her. And I said, Laura, I don't have anything up my sleeve. And Laura said, let's study causal reasoning. And I said, Laura, I think causal reasoning is not the kind of thing that has specialized brain machinery. It's very domain general. It's never going to work. All the while realizing that I had said the exact same thing to Rebecca Sachs 20-some years earlier, but never mind. I still maintain the conviction. Causal reasoning doesn't seem like the kind of thing the brain would specialize for. And then I said, okay, well, we can do both your experiment and my experiment by doing the physical versus social case and have the causal scenarios and just descriptive scenarios. And Laura can look at causal versus non-causal, and I can look at physical versus social, and everyone will be happy. And so examples of the descriptive things, the small western town had only one dirt road paved with cobblestones with small boutiques and parlors on each side. At the end of this road, a white wooden fence surrounded the perimeter of the tiny village. The vast prairie lay beyond the fence. The road was made of dirt, cobblestones, or both. Okay, just basic description, and similar for the social stuff. Okay, totally. Is that clear? Okay, so we just scan people as they read these scenarios and do these tasks. And here's what we find in the physics regions. We're looking in the left here because these are language stimuli, and there's lots of other reason to show that brain regions that are bilateral tend to respond more to language on the left side. And so here's the response to the causal physical scenarios in those physics regions, and here's the response to the causal social scenarios in those regions. So check, they are responding more to physical than social stuff. What about Laura's question about causality? And what we see is, in fact, the physics regions are much more interested in the physical causal scenarios than just the physical descriptive ones. So it may be that they're not just building models up there whenever you have a physical description to think about. Maybe you have to think about the causal structure of events up there. So that's cool. And very delightfully, the left TPJ does the opposite, responding more to causal than descriptive stuff in social scenarios. And this is pretty much Rebecca's theory of mind kind of contrasts anyway, so that's not totally new, but it's cool that it shows no differential response to causality with physics. Is that more or less clear? Okay, so that was fun. And so the answer is yes, we get engagement of at least the left parietal physics regions for causal, for causal physical phenomena in particular. But this is kind of a complicated, weird thing. So we decided to try to simplify the task. This is actually total BS. We did it in the other order, but I'm just trying to tell a coherent story. So, Laura, being a developmental psychologist, likes really simple kind of tasks that can be run on kids. So she came across this little kids game that you can do on your phone, where you have ice cream cones and ice cream scoops, and you have to match causes to their effects. And so we decided to do this in the scanner. People see something like this, and they get a little marker. So you see the effect that the boat sank, and you have to pick which of these is the cause. And so you press the 2 button, and the thing moves over there, and then you go on. Okay, so it's just matching causes to effects. Okay, and so of course we did this in 4 different ways. We matched causes to effects for physical phenomena, for social phenomena, where an example of a cause and effect are, well, let's do both cases. With a physical causal, you have to match from this array of 4. I'm not showing you all 4. The effect is coffee spilled all over the car seat. You have to match that to the car swerved to avoid the crash. That's a potential cause. In the social case, the effect is Tom was scolded by his boss, and the potential cause is he was late for work by an hour. Okay. Then we have the non-causal versions, where you have to just match things that are describing the same thing. Like, he is the head of the church, he leads the worship every Sunday. Or the closest star to the earth is the brightest object in the sky. Okay, so we had people do that task. And so first question is, does this engagement of the physics regions by language stimuli, so language stimuli, still occur in this stripped down case? And so that's a contrast of physical causal versus social causal. And then, and also does physical causal versus non-causal. So we get the effects we saw before. But then we also wanted to know, does this generalize to a new kind of, a different version of a causal question? So we used preventative cases. So for example, it's the same thing. You have 4 cases on the bottom and 4 on the top, and you have to match them. But in this case, you have to choose the thing that would have prevented that outcome rather than would have caused it. Okay, so for example, you have to match the towels were mildewed with they should have been hung out to dry, right, for the physical case, or Alice got grounded for a week with she should have come home on time. Okay, so it's just a different way to ask a causal question. We wanted to know if it would generalize to this preventative case. Oh, really, 2 minutes? Okay, it does. Everything generalized. It's amazing. Because I want to tell you one more thing. Okay, so that's pretty cool. But the last thing I want to say is I think this is all, very fun, but there's so many unanswered questions. I'll just, I'm sure you can already think of many of them. We can discuss them. But many of them are hard to answer with current methods, and that's why I'm excited about a new collaboration with Richard Anderson at Caltech. And he has this amazing scenario where he has paralyzed participants who have just volunteered to have Utah arrays implanted in their brains for brain-machine interface research. These people are really courageous heroes. They know this is not going to help them. They just do this to help with BMI research. And so they have chronically implanted electrode arrays, some of them with arrays right in the superior parietal lobe. And so we had no way to tell whether those arrays would in fact be on top of the physics network, because the arrays are actually not much bigger than 1 voxel. They're teeny tiny. The physics network is highly variable, so who knows if they would be in the right place. But I went out last fall and tested with Richard Anderson's postdoc Celia Bugu a few of these people. It was amazing. This guy kind of wheels himself into a mini mall in Los Angeles, and he's got these metal pedestals coming out of the top of his head. Celia attaches the pedestals, and there's neurons on the screen, and I'm just sitting there going, holy crap. And so we tested both our classic functional MRI contrast of towers falling versus colors, and just passive viewing of physical versus social movies, and our control generic difficulty task. And this is now average firing rate over all 96 electrodes in this little 4x4 millimeter patch of parietal lobe. And here is time, average firing rate, much higher for the physics task than the color task. Here's a single neuron showing the same thing. I, if anyone, believe that functional MRI is telling us about neural activity, but nonetheless, it's pretty cool to actually see it. For the physical versus social videos, it's even more striking. Here's the response over time, averaged over all electrodes in that array. Whopping response to just watching physical things. No response at all when watching video clips of social things. Note that lots of the brain is much more interested in the social videos than the physical videos. This region doesn't respond to them at all. Single neurons that do the same thing, and these regions don't respond to generic difficulty. Oh, sorry, one more thing, then I'll shut up. This is, we ran the prediction versus observation of collisions versus non-collisions, and we are still trying to get on top of this, but here are some individual neurons that blow my mind. Here's a single neuron in this guy's brain that responds when you, see a scenario from which you can predict a collision versus predict no collision. The same neuron responding when you see the collision versus don't see the collision. Other neurons don't discriminate, or they do it only for observation or for neither. Or here's another one that does both. And I think of the vast array of important open questions, I think this method will help us make progress. Thank you.